Hopefully, yes. Great. So thank you that you came today. For today's talk, I have prepared a presentation about my experience with early stage machine learning startups, and specifically for today's talk, I will focus more on some lessons learned we experienced during last few months, and I hope those more or less technical experiences can help you also with your startups. So this would be the main topic of the talk. Before I will jump into those lessons learned, maybe I would like to share with you my story, how I actually get to machine learning startups, because I'm building those things like 2 years from now. So in the past, I worked for Seznam. Maybe you know the company, web search company. So I was working on search engine, and specifically at the end of my time in Seznam, I was trying to shift image search on deep learning platform. It was back in like 2014, 15, something like this. So we use a lot of convolutional networks and actually tried a lot of state-of-the-art papers back in time. At the same time, guys in California from DC Venture Capital were investing into companies which were sending like small satellites, CubeSats, to the orbit, and they were thinking that, okay, we have here this cool technology, this deep learning and these satellites, so let's put it together and maybe we will be able to build some cool product, right? So that was the beginning of the story. So they asked me if I can join with my friend, and this is how it started. But like nothing was given. So in the beginning we didn't have any clear product or an idea. So we started to really think about like let's use those images to plan where to build a solar power plants, for example, or let's help insurance company to find out where the like tornadoes attacked and what damage was there, or even more crazy ideas like let's have a look on tubes with the oil, pipes with the oil which are going on the ground, and let's try to find the place where the pipes are leaking with the oil, so you can really see the spills of the oil from the satellite and tell the company, okay guys, these pipes are leaking there, so you should fix it because there is no like really robust solution for this. But at the end, it was much easier than it looks like. So we end up with a real estate market. Why so? So first of all, in the industry, specifically in the US, I will be talking about the United States. So in the US, it's a really big market with a lot of data. And it's actually quite rigid in terms that there is the technological improvement is not as big as in other industries. So to give you an idea, the real estate like is around 30% of GDP, and it gets like revenue of 340 billion dollars per year. So it's like huge industry. So we thought, okay, this is like good place where to be, where actually this machine learning stuff is really starting. And specifically, we started to focus on one simple task, which is let's have a property and let's try to estimate the value of the property. It's a really simple task, but it's actually important and interesting for many services in the area. So banks are using it for their products, insurance company as well, and even investors who invest to the real estate and have big portfolios of real estate. They are interested what's the current price of their portfolio, and this is why it's quite good to use machine learning approaches for modeling those things. Actually, in real estate in US, there still works a lot guys called appraisers who really come to your home and look on ceiling and on the equipment in the house and try to estimate the price of the property, which cannot actually scale, and they are pretty slow. and at the same time they are not so accurate, so there is a huge variance between their estimates. So again, this is one another reason why to involve machine learning into this kind of task. So well, we started really on green field, so we didn't have any data, nothing, so we started to scrape data from internet and build our custom data set with real estate and try to do proof of concept that we are able to do quite accurate predictions, at least in California, which was our starting market. And we asked banks to just let's use our predictions for your property. So what was happening is that they sent us like 50,000 of properties, and we tried to do the price estimates for those properties, and then they internally in bank look on this, and then they gave us feedback if it like makes sense or not. And actually makes sense. We were quite accurate, but the issue was that we have only scrape data. So the first question from the banks was, can you scale nationwide, like for a whole US? So, like, hell no, we were not able to scale. Even California market was kind of problem when you are scraping data from internet. So that was one issue, and we started to realize that our weak point is actually the product. That we have only really the engine which makes like good predictions, but there is nothing like extra for this. And the biggest game changer for us was that we found our CEO, guy from the industry, and he brought a vision which we are actually now trying to productionalize. So he came with the idea that we will use those accurate estimates for the mortgage business. So in the US, what is the idea? In the US, when you take the mortgage, it takes quite a long time, like 50 days, and those 50 days means like $4,000, which can be really cut off if the process would be faster. And faster means that, for example, you have really quickly the estimate of the price of the property you are taking mortgage for. So we try to leverage machine learning to make this process as short as possible, like for a few days, and really cut off those costs down. So in a big scale, when you look on the whole US, it's like 207 million wasted days per year, which we can like cut off if we have proper technology. And it's like $36 billion. This is the kind of margin you can really cut off if you would make the process faster. And right now we are building kind of mobile app which will actually guide you through taking the mortgage and try to make it really as smooth as fast as possible. We outsource a lot of solutions, but in-house we build the valuation engine. So this is the product. I don't want to talk much more about product because today it should be much more technical than product oriented. But I hope it gave you kind of idea what we are try to do. Well, for me, the first actually lesson learned from this is that even if you have really cool technology and you don't have right product, it actually doesn't work. And I know it sounds like a cliche, and I knew it, or I felt I knew it even before we started the startup, but actually I think we hit the same problem as many others, that really without very good product and business strategy, it won't work actually, even if you have really good technology. So now I would like to jump to actual research part of the project, and let's start with our flow. What is our basic flow? How we work? So it's nothing really surprising for guys from industry. Right now, we actually started to buy data because we want to really build product which we can sell. So we found our data providers, and really in that flow, first part is about really collecting data from the providers and cleaning it. It's really like messy. even if the providers will tell you that they have really the cleanest data ever. It's really mess. So we really focus on cleaning the data set. Then we do some modeling. I will talk about it in more details. We involve neural networks, gradient boosted methods to really and then ensemble all the stuff together to get an extra boost. And this is the modeling. I will dive into this a little bit more. And then we work a lot on the confidence of the predictions, because you don't want to really estimate the price of the property for the mortgage where you are not sure, because you don't want to lose the money at the end. So we focus on some confidence estimates, and actually this feedback from the results will guide us back to another data cleaning, and really this is kind of the iteration we are the loop which we are running in. So I would say nothing surprising here. We involve a lot of paper mills. I'm not sure if you know paper mill. Who knows it? Can you just raise the hand? So yeah, almost nobody. If you know Jupyter notebooks, so this is something like parameterized Jupyter notebooks. It's used, for example, by Netflix also in production. So you can run directly your Jupyter notebooks in pipelines, and the output is a kind of interactive log which you can really see what was happening, and you can take this log and execute it again. So it's really nice for researchers when you want to like analyze what were the problems. And we also experience kind of work when we do a hackathon, for example, for 2 weeks, and then try to cherry pick some good ideas and involve it to a production, which at the end made a whole kind of research / production cycle fast. So this is second takeaway, less technical. We really like paper mills and this kind of hackathon style, when you first try to really explore ideas and then cherry pick something works for us. Okay, so I will dive into each of the sections from that cycle I was talking about. I will start with the data to give you an idea what kind of data we actually have. So as I said, we are in US market, and we have approximately 150 million properties in our data set. And you can imagine that every like 3 years there is actually around 10 million sold properties, and we have a daily increment of properties which are listed, which are for sale, and which were already sold. So this is kind of a live database which is daily updated. And right now, as I said, we are in California, so there is approximately 1 million properties sold in the last 3 years, which we basically use for our training. And I'm not sure what is daily increment, but it's like thousands or tens of thousands of properties which are updated every day. And we are working with a lot of structured data. So these are collected by the appraisers actually, who really visit your home because of taxes or whatever, and really analyze what is there. And those data are then really unified by these data providers, which have like big business around just collecting the information from those appraisers nationwide and cleaning the data set and selling it to third parties. So these are the structured data. We have also structured data from multiple listings, which is actually the place where people are trying to sell their properties. And then, specifically when we were experimenting in the beginning with the project, we have a lot of other features like information about the crime, about the traffic around the property, about the floods, if it's like the safe place for building the home. We use a lot of information. We try to involve aerial images and satellite images to just extract some extra information. So at the end, the data set is quite rich. And to repeat it, the task is to take those structured and unstructured data and try to predict the price of the property, which is described by those features. So this is the task. As I said, we now use data providers, specifically 2 data providers who gave us the data. And there are a few problems with data. So first of all, and it's hopefully visible on this histogram. So as I said, we have like hundreds of features, but not all of them are really useful for modeling, specifically because they have really low coverage. So there is a plenty of missing values. So when we start the pre-processing the data, like first obvious thing what you can do is really get rid of really low coverage features, because it will cause the overfitting of the models. So this is approximately like 100 features go out from the modeling just because of those reasons. Then because of 2 providers, a lot of features are really duplicated. So when you will have a look on the correlation, some Spearman correlation here, and you will have a look what is correlated together. So you will see that, for example, we have like multiple informations about the bathroom and bedrooms. The prefix atom and FA means these 2 data providers. And it's really low-hanging fruit to just focus on those duplicated features and try to unify it. It will help the explainability to your models, and surprisingly, it also improves quite the precision of the models, even with the gradient boosted methods, which are quite robust with like duplicated and noisy data. It's fine really to try to unify in the data set. With the categorical features, because these were all continuous, we are using conditional entropy idea, how to find out which features are related together. So this is let's have x and y. These are categorical features. So you can try to calculate the entropy of x categorical feature, and then try to calculate cross entropy of x and y categorical feature, which means actually how much y explains the x feature. And it's kind of asymmetric measure of correlation of those guys. And again, here is kind of correlation matrix built on this conditional entropy. And you can again find out that there are some specifically location features which are heavily duplicated. And again, it's a good idea to spend some time and try to unify it. I mean, even if you have kind of project with structured data, this can help. So this is next lesson learned. Really try to go for a low-hanging fruit and try to unify and clean the features. Especially when you have some investors and they will ask you what was the influence of this feature. If you have this feature duplicated 5 times, it's really hard to say what exactly is the influence of fourth of the duplicate. Now I would like to talk about the labels. So this is what we are when we use this supervised training. What are actually the targets for the model? So as I said, these are the sold prices. So you can imagine that we have data from last 3 years from California, and this is the distribution of the sold prices in California. These have pretty heavy long tail here, like properties for $35 million or something like this. So this is what is actually the target for modeling, and I really recommend you, when you have these skewed distributions, to try to get rid of those long tails, which actually generates big errors and make training slower. So you can, for example, try to log scale those distributions to get kind of shape of Gaussian, which will help you. And even if you have, for example, neural networks and you have really like skewed features which go into the network, and even if you use Bayesian normalization and stuff like this, think about kind of, for example, robust scaling or other type of scaling, which will again try to normalize those distributions before you are training. I mean, I think it's kind of good idea. One issue with our training data is that those properties are distributed across the time. So, as I said, we have like 3 years window from which we take the training data. So one of the issues of the training data set is obviously that $1 million for property from, for example, 2016 is different $1 million than from 2018. So what we try to do is we try to normalize those prices across the time. So we use a house price index. This is the example how the index looks like in California. So you can see here kind of the Great Depression in 2008, 7, and then the index going up. We have also more details indexes, for example, for LA, which is in general a little bit more expensive area of California. So the green curve is a little bit higher. And when we have the properties, so these dots are actually the training properties. What we try to do before the training, we try to really normalize those properties to some specific time to really make the sold prices comparable. And then when we try to do modeling around it, the idea is that we try to correct the error of the index itself. So if you would just have this, for example, property which was sold in 2012 for some money, and you would just use the index to shift it to the current date, you will generate error of like 13%, something like this. This is the error of index itself. So what we try to do with the modeling is actually correct this error, and we will get to some 2% of actually median on a data set we have of absolute percentage error. And it's a good question if it's kind of really where you can get, because people have their natural variance when they try to buy something, because they are usually emotional, and the variance of the buyers is probably somewhere on the level that you will get those errors, and I would be surprised that you would get significantly lower than like 1.5% of absolute percentage error you can do on the prediction. So this is the house price index which we use to really normalize the properties before we train. All those techniques, like log scaling the sold prices, or even shifting the data using time index, is kind of involving the prior knowledge to your labels, and I think it's a really good idea to always try to involve some prior knowledge. So, for example, we also try normalize the sold prices with the square feet area of the property, and again, you force models to involve different type of features to do those predictions, and you can use it even in your project to try to involve some prior knowledge to your labels. Okay, with this time sensitivity of our data set, there appear also like big troubles we had during the training. One of the example which can easily happen on any data set you have, which is time dependent, is what actually happened to us. So we got data from the providers, and we have actually features for the property from I think it was year 2018, where there was kind of feature which was I named assessed value, and it was really strong feature which was really strongly correlated with actual sold price. So we had in 2018 the assessed value of the property was some number, and at the end it was sold for another price. And what happened is that in 2019 somebody came from the data provider side and adjusted this assessed value according to sold price. So those guys actually injected the future to the features, which is like really killer, because you trying to train your models on these cheating features, everything looks totally awesome, and then you go to production where those features are not updated by anybody because nobody knows the future, and suddenly it's screwed. So this is actually the scatter plot from our data set. So each dot here is the property, and there are two features. This is our target, which is log scale sold price, and here is the value of this cheating feature. And now you can see it seems pretty much correlated, but there is some variance here. But when you look on this from time perspective, you will suddenly find out that in 2018 somebody already came for 2018 and adjusted the features. That there is really, this is the diagonal, so it's really basically the target you are training. And when we have a look into the testing set, which is in the future, where this is this variance with the red dots, it was actually, the model was overfitted on this diagonal, so it had really bad results. There is no really like general way how to find this out. What you can do is, for example, trying to really train the baseline model on your data and have a look on most influencing features and then really analyze what's going on. Or you can, as we did, also set up the training and validation in a way that it would be easier to detect. So next lesson is really try to somehow, and the baseline could be a good idea, try to check that specifically with time-sensitive data, that you are not cheating, that you see into the future. And I mean, it's really common problem for a lot of projects. So I said that we have set up a kind of data set up for training that helps to find those issues. So now I would like to dive into this. Basically, we have two bunch of data. One is for testing only, and one is for training the models. The difference between those two data sets is actually time. So all the properties which we were using for testing were in the future from point of view of the training of the models. And this training set was actually divided into three parts. It's because we at the end do the ensembling, so we cannot just split it to training and validation and really do it like this. So what we did is we use this train model and validation to train kind of particular models for the ensemble, and then we use those models to make predictions over validation and train ensemble subpart of the data set. So these predictions of these partial models were actually features for the ensemble itself, which we train on those data. So why you don't want to do this on this data set? It's because here the predictions are much more optimistic than it would be in a production. So you want to really simulate the input to the ensemble as it would the distributions which would look like as in production. So that's why you have this extra training data set. And this is how we actually do it. And this is also how we really find out that we have the cheating features, because on the test set which was in the future in 2019, suddenly the models started to work really badly in comparison to validation set which was still cheating. So lesson 6, really try to simulate everything you would have in production. I know it's hard, but try to think about each small detail. You can have it there, because at the end when you will jump to the production, you won't be sure that the metrics you are reporting to your investors or anybody else actually hold in production and are not biased by something. Okay, so this was about the data itself. Now I would like to jump a little bit into the modeling part. So as I said, we do the ensembling. we ensemble basically 2 type or 3 type of neural networks and gradient boosted. So we ensemble neural networks and gradient boosted forests. These are 2 major approaches we are using. We also tried to involve images with some deep convolution neural networks. And the idea here is actually that we try to combine the approach of boosted trees, which from the perspective of how the models manipulate with data in space, they are really cutting the data and are pretty much into some subclasses and are pretty much robust with noisy data and stuff like this. And neural networks are much more sensitive. We try to build some rich embeddings around categorical features. This is the idea which we have. It's inspired by fast AI and TabNet, for example, approaches. So we try to build some rich embeddings around categorical features, which we hope it will help. And then there are image models, which again try to build embeddings around the aerial images. I will talk maybe about this in a few minutes. So I will start with the neural networks, but since we don't have enough time, I will let you vote what you would be interested more. So we have 2 options. One option is that I will talk about the structured data, how we approach it with neural networks, and I will mention a few fast AI tricks which we use. And second option for you is that I will talk a little bit about the imagery data and how we approach the images. So first is who is for structured data? And who is for images? So structured data won actually. So I will talk a little bit about this. We try to involve 2 tricks from actually Fast AI and Jeremy Howard. One is, and I am not sure how it's called. It's learning rate range test. This idea is about searching the optimal learning rate for your neural network. It's kind of heuristic. And what you can do is that you can take your data, your model, initialize, and start to train. And with each batch, you start with a really low learning rate, so it's on the left. And with each batch, you increase your learning rate, and you really build this curve when on y-axis is loss. So here on the right, from your perspective, there was such huge learning rate that everything exploded, and there was a huge loss at the end. And the empirical experience is that if you will take the learning rate which is on the biggest slope on this blue curve, which is actually just this red dot, and it's not really in the minima, but kind of a little bit on the left. It's really fuzzy, but this is how it's interpreted in Fast AI. It will give you reasonably big learning rate, which will still guide you to the optimum, but it would be fast. So this is one of the ideas we use. And another idea is about one cycle learning. This is from old paper from Leslie Smith, but it was again evangelized by Jeremy Howard. And the idea is that when you start to train, you start with really low learning rate, and actually the learning rate is somewhere from this. This is the starting point, and you slowly increase the learning rate to the peak, which is actually somewhere here, and then you again start to make learning rate smaller. So what's the idea? The idea is that in the beginning you will try to find some area with local minima. then you will let the model explore, so you won't just be locked on some saddle points, and then you will actually end up with really small learning rate, which will adjust the final results. And Leslie Smith actually used in her paper also idea with momentum. So in the beginning you have really big momentum, which means that you are really conservative, and when you are on the top here, you have really you have big learning rate and really small momentum, so you really enforce the model to explore, and again at the end you shift to really exploitation, the solution. And they in the paper they demonstrated actually on image problem. So they were, I need to read it because I don't remember, but they were training I believe ResNet and on ImageNet, and in 60,000 iterations they got to kind of let's say state-of-the-art results, and then they involved this approach, and they use just 10,000 iterations to get to the same result, and with just 50 iteration they got really like 1 percentage point lower than the state-of-the-art. So it really makes the training faster, and this is what we use, and it works. I added to the presentation the actual original paper from Leslie Smith if you are interested. So with the neural networks on structured data, we try to build really embeddings on categorical features, which is one of the idea from FastAI, and then use this one cycle strategy, makes things really faster. This is the experience. I will skip everything about the images. I'm sorry. But the idea is that we try to fine-tune the neural networks on those kind of aerial images. When we fine-tune, the target is median price of the properties on that square, and then we try to involve the embeddings or the predictions to the ensemble. That's the main idea, and it didn't improve almost at all the median of the absolute percentage error, but it improves the variance of the modeling. So basically it tries to fix the long tails of the distribution, not the median. So it didn't improve yeah, the accuracy, more or less it improves just the edge cases. Okay, last part of my talk will be dedicated to gradient boosted methods and to hyperparameter optimization of those methods. So we use a lot of LightGBM and CatBoost. Who actually knows those approaches? Can you just raise your hand? Again, almost nobody. It's interesting. So I really recommend. I have some recommendation around papers you can read. So no worries. High level idea of gradient boosted forest is that you build kind of trees, and when you try to evaluate some property, you take the features of the property, and in each node of this decision tree there is some decision around the value of some feature, and according to those decisions you will end up in some leaf. In those leaves there are scores which are at the end sum up, and this is the prediction. It could be weighted or whatever. So this is the prediction, and what you can do actually is you can calculate the loss of this kind of ensemble of trees, and what you can also do, you can calculate the gradient of the error with respect to the predictions or just second derivative, and those guys, this G and H, those derivatives are actually drivers for building another tree in the ensemble. This is just the high level idea of gradient boosting ensembling. So when you try to build another tree, the tree actually try to predict something like negative or something which is similar to negative of the gradient, because the gradient, the negative of gradient will point into the local minima. So this is the simple idea. If you are interested more in some like nice explanation, you can add there the link for XGBoost paper, for example. There are all derivations on two papers, how to really decide what would be in a decision rule and what would be the values it leaves. That's the whole idea, and it's nice. So recommend it. Like in a few years, these gradient methods actually improve a lot because Yandex tried to build their decision forest with a CatBoost. Microsoft is like pushing with the LightGBM, so there is a lot of good ideas. I don't want to mention too much because again I think it's more or less on each of the ideas on single talk. So I would mention just two of them, and then the rest would be for you if you are interested. I will show you the sources. So one of the ideas of the CatBoost is actually that it builds something which is called target statistic. The idea is that when you have categorical feature and it has a lot of categories, how to represent it in the data. So you can have, for example, 100 encoding of this categorical feature, but it would be like huge, data would be sparse. So what CatBoost automatically do, and maybe you did it in your data set inherently, is that it calculates target statistics. So I will give you a concrete example with categorical feature zip code. So zip code in our data represents some geographical area, and we have plenty of zip codes. And what we can do, we can substitute the zip code with average sold price in that area and represent it rather like continuous feature. You need to check some things like when you have concrete property, you don't want to include its sold price into its target statistic because then you are cheating. So there are small catches you need to focus on. But this is about like building target statistic, which is automatically done in those frameworks. Then they, for example, use gradient one-side sampling, which is about making training faster by selecting just the examples with the biggest gradient for next iteration of building next tree in the forest. And there are like a lot of cool ideas. I leave there some references, so if you are interested in more details, or even after the talk, come to me and I can give you overview about this, but I won't dive into much more. So what is the catch for the gradient boosted methods, which are great for this type of problem? Is that it has a lot of hyperparameters you need to set up, so you need to think about how deep the trees would be, what would be the learning rate, what would be regularization, how many leaves you want to have in the trees, and all of this somehow affects the results. So how to fix it? We use something which is called HyperParameter Optimization to really find out the good set of hyperparameters before training. The reason why we need some extra approach for this is that if you would just try to set up some parameters and run the gradient boosting methods on the training data set and then look how it went and then try another set of hyperparameters, it would take quite a long time. So this is expensive from time perspective. So what we do with the hyperparameter optimization, and by the way we use is Ray and HyperOpt tooling, so you can have a look. Again, there are the links. So what we try to do is we try to build the simulation of our expensive model with something which is called surrogate model. So in this example I'm using here is that we have one parameter we want to optimize. It's on x-axis. On y-axis is actually the loss, and the blue curve here is the true loss of our model. So if we would just run the expensive model for each parameter, we would get those losses, but it would take a long time. So we have just a few samples, which are the red dots, which were actually true runs of this expensive model. And what we try to do is we try to simulate how the loss would look like for another parameters. And for example, we can use Gaussian process. I'm not sure if you know Gaussian processes, but you can imagine that it's like kind of multivariate Gaussian, when each dimension of the Gaussian is one run of one of these red dots, and you can sample from this Gaussian, and the sampling are these yellow lines, which are kind of predictions how the loss could look like in different points than the red dots. And you can really calculate the mean and variance of the expectation for each parameter. So this is kind of modeling with Gaussian processes, how to really in fast manner decide what could be the next point we would like to sample and run the expensive model on to find the best hyperparameters. So you need probably some function which will involve this Gaussian process and will help you to navigate which point would be the best, which will cause the, for example, best expected improvement of the loss. And then actually when you start with the running, you really according to Gaussian select another hyperparameter, then you evaluate this loss, this function which will tell you what is the next best parameter for sampling, and you really in this faster manner you can find the best hyperparameters. Why I'm talking about it here is that it was kind of really huge surprise how bad and good hyperparameter setup can affect your final results. So I prepared really small experiment, and it's really the last part of the talk, which I hope will demonstrate how important it is to have right hyperparameter setup in your gradient boosted method. So what I did is I had 3 models. One is baseline model, so I really take LightGB and some default parameters which were how it is pre-configured. And then I prepared two data sets, and both of them were on the real estate data, on our data. And the only difference between weak and strong data set was one feature, which is really strongly correlated with the target. So in the weak data set, there were some basic features about like how the property is big, how it's old, how many bathrooms it has, pretty basic features. So it was the weak data set. Strong data set was completely similar, but there was one extra feature which was strongly correlated with the sold price, with our target. And then I trained the weak model on a weak data set, the strong model on the strong data set, and not trained, but I tried to find the hyperparameters. And I will give you one example, but all other examples here end up with the same result. So these are the hyperparameters actually which you set up in your model. And for example, when we will have a look on a number of leaves, which is really how the maximum of leaves you can have in one tree in the forest. And this is the distribution from which we sample. The result end up like this. So the weak model was really forced for kind of overfitting. So we let this weak model to build really deep trees because the hyperparameter search tried to really enforce the model to find better solutions. In contrast to this, when you have one strong feature, the parameter of number of leaves for the strong model was only 3 leaves, so it was highly regularized, and really the hyperparameter search tried to set up the setup for training in a way that it won't overfit by no means, because there was one strong feature, so that was the threat that these models would overfit. And actually it ended up in the same way, the same message from all the features. So in case, yeah, and I also leave here some some other results, but the messages would be like simple. The model which was optimized for the data set had the best results on the data set. I used something which is called median absolute percentage error, which means that I do the prediction with the model, calculate how many percent the prediction is off, and then I looked on a median of this value across the data set. And when you have a look how it end up, so baseline on, for example, weekday data set, it has 7.2% of error. Model which was tuned on the strong data set, it has even worse results than baseline. And when we have a look on model which was tuned on weak data set, the results were best. The same is with the strong data set. My takeaway here is that, for example, if you have a look on Kaggle competition and you think, okay, these are great parameters for that problem on Kaggle, and I have the similar problem, and I will just take those hyperparameters and like I have the best possible solution. No, you don't. I mean, this is kind of proof. You can have like good solution, but always think about really run some hyperparameter search, and I am pretty sure that you can find a slightly better setup for your particular problem, even if it's really similar to someone else's problem, which is like published somewhere. Try to play with the hyperparameters, and for us it was quite surprisingly big improvement. And this is actually last lesson learned from our research on real estate, and it's really focused on your hyperparameters, and yeah, it's again low-hanging fruit. So here is the summary of the lessons learned I was talking about. Always think about the product. I know it's boring, but at the end, the technology, I believe, is not enough. Focus on your features, like cleaning and unifying stuff. It's easy, and it will bring you really better explainability to your models, and it will make the results slightly better. Always try to simulate your production in all details, specifically when you have time involved. Look on FastAI. I mean, they have good tricks, and it's kind of like practical tricks for specifically for neural networks. So it's good source for inspiration. Try to work with your categorical features. I think that it's also weak part of many like really automated solution online. I'm not sure if H2O has something stronger, but I know that maybe Teapot is really weak with the categorical features. So try to focus on this, building embeddings, or nowadays the boosted methods are pretty good with this. So that's it. And last but not least, always optimize your models for specific feature set. It really helps. And actually that's it. Next time probably with some lessons learned from our production, and thank you for your attention. Jo, určitě. Normálně to tady jsem cast, tam tady klikni sem. A tady ten cast, tady. A já nevím, jestli si tam přihlásíš, ale zkus a normálně začneš shareovat. A to, já myslím, že tady to na space. A tady se otevří nový tab a už si tam co potřebuješ, ale já tam nemůžu odbrbat. Ještě to budeš muset vykastovat potom. rozptýlnutím klosku. Aha, zprva. Cool. So, should I be the moderator of the discussion, or? So maybe if you have questions from the audience, just raise your hand. Maybe it's better, and if not, we will use the Slido. So, are there any like direct questions? Maybe not. So I will start with the anonymous ones. Do you only use info about the housing market, or also macroeconomic variables? We use more or less just the housing information. We have also data about the mortgages and stuff like this, but the only macroeconomic variables or information comes from the index price indexes right now, so nothing more. Yeah. Second question, is XGBoost the best boosting algorithm? I think when I look on the comparison, and yesterday I read the paper about Tabnet, which is quite cool stuff. If you don't know it, it's about neural networks which are finally good enough. At least the paper claims it on the structured data. The XGBoost goes on par with LightGBM. But from our experience, at least when we were doing prototyping, LightGBM was much faster to train, like really much faster. But from all papers I read, usually XGBoost comes as a winner, but it's pretty tight. And CatBoost is usually on a third place if it's not the paper from CatBoost authors where they claim that it's the best. My experience is that LightGBM works for us the best. Have you considered AutoML for finding the architectures? Yes, we did, and actually it's not so long that we tried to use also a H2O and also AutoML to tune our models. And it seems that still with AutoML, I believe it really depends how much time you will let it optimize. And I won't tell you from the top of my head how long we let it. So maybe it's unfair for AutoML, but still we are able to bring the best results by ourselves. But I mean it's a matter of like year or two when even on our problems they would be superior. I mean, the big advantage of us right now is in like really custom feature pre-processing and small tricks with the labels we do, because it's really like problem specific, and I'm not sure if the AutoML or another automated solution really is able to solve without the human expert right now. Maybe you know guys, so you can tell, but I think this is still the slight advantage of us, that we can really customize it for our specific problem. But otherwise, when you look to the this I would call it black boxes, which are as a commodity, they don't do any much different than we are doing. They are ensembling solutions using like combination of neural networks and boosted trees. I'm not talking specifically about AutoML, but also other providers involving some HyperOpt stuff or another HyperParameter optimization. So I mean, it could be pretty close when for a lot of problems this would be solution, and really like feasible solution for industries. So. I go to the next. If there is not a question from audience, I prefer the question from audience actually. Nobody seems that has courage to ask something, so I will go to anonymous one. Does it matter what particular cyclic learning rate schedule are you using? Do you need to use some funky curve or just cosine with linear warm starting? To be honest, we didn't experiment with this much. So we actually adapted what is in Fast AI, and it worked well. So nothing specific to this question. Maybe if the person who asked came to me after this session, and we can discuss deeper. But honestly, we didn't elaborate on this much. So I could go to next. Do you think that your method has potential to take over traditional real estate evaluation? I mean, this is already happening because there is some competition which is using, I believe, kind of similar approaches. For example, Zillow or Redfin, or those guys who are actually started as real estate like providers and did their estimates, and nowadays they really shift their business for buying the houses, and really they are leveraging these estimation engines for multiple things. So I mean, this is already happening, and we are definitely not the first, and definitely not the last ones who are focusing on this. I mean, really it would be also about finding right product for these estimation methods, because I think that basically everybody does a pretty much similar thing. Some of the guys do a little bit better, some of them a little bit worse. The data sets are pretty much similar because we know who are the data providers, and there are not too much extra data which won't be involved. We thought that images would be the real game changer. It's not the game changer, more or less fancy thing. So yeah, that's it. What are the hot trends in AI now? Wow, so I can address some of things which I think. So first, maybe I can look back for on last year, which was the year of NLP from my perspective, when the transformer and BERT and other approaches based on attention came to the NLP work. So this was definitely the year of NLP. And I mean, people start to think much more about building semi-supervised modeling, because they have unlabeled data, so a lot of unlabeled data. So leveraging those things to the data set is definitely a big topic. Another big topic is definitely connected also with the self-driving cars and with the image processing, because we started to realize that the adversarial attacks and basically the way how we're training the image neural networks can cause some problems, and really, I mean, the image area is good area to think about, because it was so fastly adopted by industry, and right now people started to think about like the side effects, so what it can cause. So I think this discussion was kicked off by some papers like adversarial attacks, when just guys were able to emulate some stickers, and when you put the sticker to anything, the image neural network was predicting that it's something like toaster or whatever it is. And people start thinking, okay, so what if I will just do this artificial sticker and put it on a stop sign, and my self-driving car wouldn't just recognize what is on this sign. So this is like big part of the discussion these days, and I expect that 2020 would be the year when people will focus on these adversarial attacks. Yeah, and definitely hot topic is still the reinforcement learning. Even we saw a lot of advances with playing the games. I think the hype still exists. I'm not sure if it's like practical thing, but people are really definitely interested and try to publish papers about it. Yeah. Yeah, sure.
Are the investors already kind of concerned about the sort of adversarial uses? Somebody will just try to sort of build a system, and so whether the arms race is already on, so you basically make the estimation, and then the other guys will try.
We are worried. Investors not too much because I mean because like my experience is that there are not too many of them who are like very familiar with the technology. For a lot of investors, it's still like kind of black box. So.
But by the way, how would you know, right? Because I mean, the house is already sold. So if somebody's fooled to overpay the price, I mean, how would you get a signal sort of? You know what I mean?
So
if somebody has this adversarial system which tries to basically overprice the houses, and when that sort of the money changes the hands, so the price has been paid, so that's now the real market price, and you would never really figure out that you are fooled, right? Because there's an error.
Yeah. And we were thinking about these adversarial attacks because, as I said, we use the images and for example, interior images, and it's like good example how to bring the adversarial attacks to this.
Airbnb thing, like, oh,
Yeah, exactly. And we also try to use, for example, some descriptions with NLP stuff and like look on the sentiment or whatever it is. Yeah, and this is problem. We still like there is kind of safe space in a way that, for example, the imagery which is provided by data providers, it's done by the appraisal, like the certificate guy who is making the picture. So there is still some like certainty that, yeah, quality control. But yeah, this is also like a topic for us. But investors are not concerned. Yeah. So next one, do you trust academic paper without provided code to experiment? No. Would you put time, money, effort to try to reproduce their results? No. I mean, this double no. It's always suspicious when there is no when the data set doesn't exist and when the code doesn't exist. So. Yeah, and I mean, there is an archive with just papers which has reproducible code, for example. So, I mean, I would definitely not waste time to try something which I don't have reproducer for. And there sometimes there are papers, and I have said that there is no reproducer. I definitely sometimes read it, but you know. Then you need to ask yourself why the code doesn't exist or what's going on. So I think it's becoming standard because you know the industry changed a lot, like the machine learning space. Because you know, for example, when you have ability to build your stuff in some framework which we all are somehow like using, like PyTorch or whatever it is, and it's not so old. Like in 2015, I think it's first release of TensorFlow or something like this. So it changed a lot in a way that people really can reproduce their work, and yeah, it helped industry a lot, I think. So did you have to implement those tricks on your own, or are they already parts of some libraries? Well, a lot of tricks are somewhere in libraries or on some other GitHubs, so people try to implement a lot of stuff. So you can use this, and I would say that we use a lot of those sources. I'm trying to think about really some tricks which we implement by ourselves, more or less. The good example is, for example, this subnet paper which we read like really yesterday,
and it has reproducible code, so we will definitely like play with it and try to integrate it to the code base. I don't think that we would be implementing it from scratch or something like this. So yeah, we try to use what is prepared. Can you possibly use your knowledge and information to predict crises in a real estate market? No, I think that we don't have those kind of information in the modeling, so it could be kind of a blind spot of the approach. I would be surprised if anybody would like seriously do this. Like for example, like checking like Twitter and social media and whatever it is, and build the features which could help to predict. Okay, we are going to crisis. So answer is no. Next one, how much is train ensemble better than just average of models? I don't have the concrete number, but it's not much. It's not much, but I feel we are like in clear competition with our problem. We're really like hunting the half of percentage point. It's like significant improvement. So average would be definitely good baseline for the ensemble, and I wouldn't say that like the training, the ensemble itself would improve it much. Like definitely it won't improve it for 1 percentage point. It's not the case. So the average would be itself, it would be very good. Have you tried other hyperparameter search algorithm like successive halving or population-based methods? No. I think it's is the answer. No, we actually use the HyperOpt, which doesn't use Gaussian processes as the engine, but Parson tree estimators. So the model doesn't predict the probability of loss given the parameter, but it factorizes this thing into calculating the probability of kind of loss and then probability of hyperparameter distribution given the loss. So it's just math and it works. Yeah, that's it. We are done with Slido, but maybe some questions came to your mind during the time I was speaking, or maybe you are super hungry and I see the pizza there, so.
I will one more. You mentioned that the investor might ask you about the importance of features, but not the case, right? Or do they ask you? Do they give you some threshold like this, like okay, we will give you this parameter, probably this, and I will tell them the guy who does the assessment?
So they don't ask during like investor call, for example, when you really try to pitch your idea. But what happens is that they will tell you, we have like data analytic department, we will send you something and you will give us, for example, predictions, or you will tell us what you think that is most important for your modeling. So in this way, yes. But it usually doesn't happen that the investor itself will ask. This guy has like exactly, and they usually bring them with them to the meeting, or you will just send them the stuff and they will decide afterwards. This is my experience. I am not sure if it's like general true, but.
Any question? If not, thank you. This was really exhausting discussion. One big applause for Adam and his talk.
Thank you.
Right now, the last thing. We got some surprise for you. Give me a second. Next month there will be the biggest machine learning conference in this part of Europe, and we got a coupon for you if you want to attend. It's in Prague, starting March 20. Right now, please don't rush away. There is a lot of pizza behind you and some drinks for you too. One more applause and thank you for coming. See you in March.